So this session is on the benefits of smart contracts.
All right, thank you, Julia. So just in the last session, we talked about blockchain technology as it relates to smart contracts and how blockchain technology has enabled smart contracts to be deployed and further live up to some of the initial dreams that folks like Nick Szabo had in the 90s of having business processes and in some cases replacing legal contracts with code that executes in semi-trusted and untrusted environments, enforcing contractual agreements and clauses between different counterparties. And so just to recap that before we dive into some of the benefits, if you recall, smart contracts, it's a concept that was developed prior to blockchain technology, and the goal there is to enable to enforce contractual agreements through computer code. And with blockchain technology, we are now seeing a resurgence of interest in smart contracts, and it's allowing the concept to actually be used today in enterprise processes, which is what Luther is doing. And at a high level, the key benefits of smart contracts from a really high level, and then we'll start to drill down and talk in more details. But really, the three key benefits is increased transparency. So this allows these different participants to have more visibility into the details of their contract and how their contract, in some cases, is being executed. So it allows all the counterparties to see and be on the same page and have transparency into that process. We'll dive into that, how that relates to enterprise business processes. The second benefit was reduced counterparty risk, which because the counterparties no longer have to necessarily trust each other or trust a single third party, they can now engage and enforce the contract amongst themselves through very clear code, and that allows them to be more sure that that what they think they agree upon is exactly what they agree upon, and as events happen in the real world, the right contractual clauses are triggered, and that they're all on the same page, and they're not having to fear that some trusted third party either incorrectly monitors or executes the contract, or in some cases if the trusted third party disappears, maybe they go bankrupt, what have you. It allows this smart contracts executed on blockchain technology allows the counterparties to, in a peer-to-peer way, execute their smart contract without the requirement of that trusted third party. And then the third one is just increased efficiency. So in many cases, when you do have like a lot of previous, typically in enterprise processes, you would have a trusted third party. So if for example, during the execution of interest rate swap, you would have a swap execution facility, which the different counterparties would submit their interest rate swap details to, and then they would, the swap execution facility would then go and process those swaps. And by taking out the middleman, as it were, you can reduce the amount of in addition to the other benefits, you can reduce the amount of time it takes to process that interest rate swap. So they can do it directly with between each. The counterparties can do it directly between each other without having the delays in processing of going through another intermediary and another round of processing by this intermediary. So at a very high level, those are the key benefits of smart contracts, and at a high level conceptually. And now let's start to dig down into how that applies to business processes specifically, and how Luther Systems is leveraging smart contracts to provide products for our customers. So going back to the transparency benefit, high-level transparency benefit. So one thing that a blockchain architecture provides is a single source of truth of data. So in many enterprise and mega corporations environments, you end up with many different systems. Each system might have its own group or IT team that manages and maintains that system. There's probably a database that's storing records as part of the system. And what ends up happening is you have this spider web of different teams and different technologies and databases, and then you have point-to-point custom integrations between those databases. And that can be within a large enterprise, and it also happens across different enterprises and companies. And we'll probably explore this concept in more detail in subsequent sessions. But you end up with this spider web, or what we call a fractured ecosystem, where it's all these point-to-point integrations of custom proprietary technologies and databases, and then these point-to-point integrations, what they're doing is they're executing a business process that touches these different touch points, and is updating these databases as the process executes. So if you think of, let's say, an invoice for an insurance claim processing pipeline, one system might receive an invoice from a customer from a web form that the customer types in, and then that invoice is getting sent off to another system that's then determining whether or not there's a corresponding estimate message that's received from a supplier, and then there's a separate payment system that these messages would end up being sent to, and so these three different parties, they would each have their own systems and their own databases, and as part of that, they would have their systems are having to reconcile their databases and make sure that they're in sync, and that introduces a lot of inefficiencies. So you have and these databases fall out of sync, and you end up getting errors and delays in processing. And in many cases, you don't catch the error until the very end of the process, and the customer hasn't been paid yet, and they're on the phone with customer support, and then all these teams are scrambling to figure out what went wrong and why the customer didn't get paid or didn't receive their missing item. And so having a single source of truth where all the participants within, let's say, both an insurance company and its supplier, or separate groups within an insurance company, having them on a system where they all that they know that their databases are in sync, provides a lot of value for them, and so that there's no ambiguity as to does my database say something different than your database, and so single source of truth allows these different groups to keep and to maintain. Importantly, they each maintain still their own system. They can keep their own IT group. They don't have to give that up to some other group. But those systems are now kept in sync through, let's say, a blockchain network that's ensuring that their data is in sync and provides them a single source of truth of that data. So that's from the perspective of accessing data, knowing that the data that they're reading is going to be the same data that the different groups on the network or participants on the network or touch points, it's going to be the same. They're all going to be seeing and reading the same thing. By encoding business logic in your smart contract, you can also make sure that the data is being processed consistently. And that gets into a second key benefit of smart contracts is data validation and verification. So going back to our claims processing example, so now instead of having the validation of the claim process be something that is broken into 4 or 5 different systems happening at different times, you can encode and capture those business rules, those data validation and verification rules within the smart contract. And in that case, the blockchain network will validate all the data that the smart contract receives. So let's say an estimate and an invoice. And it'll do that in a visible and transparent way so that all the parties, they can see that processing. And in fact, all their nodes are, when they participate in this network, their nodes are running this program, this smart contract that's executing these validation and verification rules and making sure that the data is correct. And then they reach consensus on the execution of those, so that they're all in agreement as to each execution step of the data validation and verification. So in your invoice, in this claim processing example, no longer is it the case where, okay, this system, the web portal system that receives the claim does some custom or does some logic to check to make sure that the fields there's no missing field, let's say. And then over in this other system, you're checking to see if that there's an invoice number that matches some other format, and the business logic is sort of spread across 4 or 5 different systems. Now you can capture all of those validation rules within a single smart contract that executes across all the different groups as part of this process. And as soon as something goes wrong, all the participants can see that, and they can see exactly why, what the problem is, when it happened, so the timestamp, what validation rule failed, and there's no ambiguity as to what the source of the exception or the error or validation problem was. And so if you have, in some cases we've seen like insurer and supplier relationships where there's sort of this back and forth where the supplier says, well, I sent you the message and it looked good to us, and then the insurer says, well, either we didn't get the message or the message is missing these fields, and it's sort of a he said, she said scenario. Whereas by encoding all those business rules and having the events and their timestamps all in a single place, as well as the verification of those all encoded on the blockchain, all the participants, the insurer, the suppliers, they all can see exactly what's happening, and there's no ambiguity. It no longer becomes a he said, she said. And importantly, as the different participants are providing data to these smart contracts, so they're creating transactions on the blockchain network. Those transactions that they create, they use public and private keys and cryptography and digital signatures, so that you have. So essentially, it's impossible to forge the identity or the of who is issuing these transactions and the timestamps of when they were issued. So you have these non-repudiation guarantees. So the blockchain network is enforcing this to make so that not only can everyone see, but using sort of modern cryptography, you have non-repudiation so that they can't. Everyone is committing to that series of events and that event history, and using their private keys to sign that they are issuing those events. And if they're the only one that controls the private keys, then they are clearly the responsible party for introducing that to the system, and everyone's on the same page. So it's going back to the transparency. So that brings us to security. So the blockchain network is enforcing the data validation the access control, all of these rules, the execution, the consensus, all of this is backed by modern cryptography, and in Luther Systems' case, this is cryptography that's this isn't like new or experimental. It's pretty well understood cryptography, just being recast in the specific blockchain architecture. And as I said before, you get non-repudiation, so that every event or every processing step is attributable to an identity that's known on the network. So we're talking about permission blockchains here. So in order for a participant, what we also call a touch point, to gain access to the network, to create transactions and send those transactions to smart contracts, to query the blockchain, all of this requires the individual or the organization, the touch point, to go through an authentication step where they have to identify themselves, and that uses your traditional cryptography, where there's certificate authorities, and each group has public and private keys that are signed by these agreed upon certificate authorities. And when you issue transactions, those are also signed, and in some cases the data is encrypted with these keys as well, to provide confidentiality. And then most importantly is the consensus algorithm. So the way that all the participants reach agreement and know that they're on the same page is that is part of this architecture. When someone issues a transaction that sends data to a smart contract, for the smart contract to process that data, let's say execute some data validation rules, maybe trigger some events. The way in the architecture the transaction gets executed across a number of blockchain peers. Those peers endorse the transaction, and then the transaction gets submitted to the network and ordered. And as part of this process, this is where consensus comes in and ensures that all the participants in the network reach agreement as to the execution of that transaction, what the resulting updates to the underlying databases are, so that they're all synchronized. All the nodes are synchronized and see the same thing. So that and these consensus algorithms, in some cases, are what are called Byzantine fault tolerant, and all that means is that not only do they support nodes crashing, so you need to be able to support cases where, let's say, one of their servers goes down, someone tripped over the power cable and their server's off. Like the network needs to continue to operate in those cases, and the consensus algorithms are able to continue to run, and the network is able to continue to operate when a node crashes. But in addition to crashes, that's called crash fault tolerance. The network should support Byzantine fault tolerance, where nodes may lie to each other as part of the consensus algorithm. So a node may tell one of its neighbors that the transaction was valid, and then it might tell another one of its neighbors that the transaction is invalid, to try to confuse the consensus process. And Byzantine fault tolerant consensus algorithms are able to support a certain percentage of the nodes misbehaving. And that's important, especially in cases where you have a network composed of different organizations that are semi-trusted or untrusted. They might be competitors. If you think of an insurance fraud case where you have competing insurance companies on the same network, they are competitors. And it's not necessarily the case that you're worried about one insurer trying to break into another insurer, because there's sort of or contractual agreements between these, and they would just report that to the authorities and legislate that. But it could be the case that you're worried that you're happy with your IT department's information security team, but maybe you don't trust your competitor's information security team. Maybe you think they don't have as strong security as you do, and so you still want to be able to protect yourself in the case that someone else's server gets hijacked and does try to attack the network. And that's where these Byzantine fault-tolerant consensus algorithms provide protection against a certain number of nodes misbehaving in the network. A certain number meaning, think on the order of like a third of the nodes misbehaving, like in a malicious way. Going on to the next benefit. So we mentioned the increased efficiency that smart contracts provide. So digging into that, going back to the interest rate swap example that we talked about. So blockchain technologies are a peer-to-peer technology, and that means the participants are each, which again could be separate organizations, it could be multiple groups within an organization. It's a really large organization. Each of those groups have their own servers, and those servers are just computers that are running this blockchain software. And the blockchain software is then executing these smart contracts. And so what this means is that there's no longer a requirement of this trusted third party. So in the swap execution facility case, the several banks would agree on an execution facility, and they would put the trust in that execution facility to execute the swap. And the problem with that mainly is that the swap execution facility can extract high fees for performing those services. There's sort of information asymmetry. They get a lot of information about the entire network, more than in some cases the individual banks. So they get information from multiple banks, and there's a lack of transparency in how they operate and what they're doing. So these counterparties don't get to peer inside the execution facility and see what they're doing, so they can't really get a good understanding of whether their transactions are being executed in an efficient way or in a proper way, So you end up with the delays, the higher fees, and lack of transparency, and increasing risk. And by blockchain technology and with smart contracts, it allows, in this case, like that middleman, the intermediary, to be cut out, and the banks can engage and perform those functions between each other directly, and cutting out the middleman. And that disintermediation, cutting out the middleman, is in general one of the key benefits of smart contracts. And ultimately, that leads to reduced costs by having more control over the process and visibility, and not going through these intermediaries, which can be quite powerful. So in many cases, you see these intermediaries having very entrenched positions and being able to charge very high fees. You end up with cost savings, and then of course, if you're able to execute transactions directly and do that more efficiently and faster, then in some cases you have reduced settlement times. So you're saving money by having more money available and less money locked up in processing and waiting for these transactions to confirm or complete. Going back to the error reduction, so efficiency and error reduction. What so in the invoice processing case, by having the smart contract encode those validation rules and capture them, you can catch the errors. You can push the error validation much further up in the process. So instead of waiting for a customer to send an angry email or an angry phone call, the smart contract can do the validation as soon as it receives the data. Any of the data provided by any of the touch points, it can do that validation immediately, and you end up with an event history. So if you look at a claim, which would receive estimates and invoices, each individual claim would have a list of events that's stored on the blockchain, where events are triggered either by the smart contract processing data, making a decision of notifying some other touch point, or deciding that the contract, that the invoice needs processing by some touch point, or an event is triggered off the blockchain. You have a claim waiting to receive an invoice, and then a supplier connects to the network and creates a transaction with that invoice, raising an event. All of the event history and the timestamps would be captured for that claim in a way that has provenance of the history of the processing of the claim. And you can do these validation and these checks immediately as soon as the data is provided to the smart contract, instead of having a process that introduces errors and having those errors propagate across various systems, and then trying to troubleshoot where the origin of the error was, who initially introduced the error. That's a big problem we've seen in the past, where you go on these expeditions of trying to find the root cause of an error, and that's why you see teams of 60 people emailing on the phone, calling suppliers, trying to understand where the error was introduced because of lack of transparency and visibility in the process. And so by capturing those error cases into the smart contract, you can see exactly at what moment in time the error was introduced and by whom. And it's important to note that there's always what we found is that in many cases you can capture many different error cases in the smart contract, but there's still going to be some error cases that may require manual intervention. So you can do a lot of automation in terms of raising errors, capturing errors, automating a response to errors, notifying the right people. But in some cases, there are conditions where you want to have an individual be a man in the loop, so to speak, to manually investigate. So you would flag a claim, and in your smart contract, you would encode this logic. So you would classify the different types of errors that can be introduced in the system, and their responses, how you would handle if that error was raised. Maybe you're sending a notification message to a manager that would then subsequently investigate. The smart contract can also can flag claims and wait for a manual response from someone to provide their input. So if the smart contract's not sure whether that there's an error, for example, then they could raise an event notifying a claims manager to then log into the system, manually inspect the claim, and then provide their input in order for it to then proceed and complete its processing. So we found that most in the business processes that we've looked at, adhere to their systems, about 90% of the errors that these processes have, we can capture and automate responses for and handle gracefully. And then there's another 10% or so that would require manual inspection and intervention to then follow up and investigate. But importantly, the smart contract is driving that process. So the smart contract is still capturing that. It's notifying the individual when they need to do that subsequent investigation, and it's capturing their response to that. Even in automated processes, you can capture. Even in automated processes, let's say payments, there are many subtle error conditions which which we found that smart contracts can monitor and follow up on. So to give you an example, when triggering payments as part of this claim processing application, there's the smart contract triggering a payment to some external systems. Let's say it's over some kind of SOAP XML API. There's determining whether that external system received the trigger payment message. So the smart contract needs to make sure that that external system received that trigger payment message. So there might be a timeout. The smart contract can keep track of when it sent the message, how long to wait before raising an exception. If it receives a response from that external payments system that the payment was triggered, then it might trigger another timeout to wait for a payment complete message provided by that external system. So those types you can capture in integrating different systems like payment systems. The smart contract can drive the process and have rules that track things like when payments were made and setting timers and making sure that that responses are being received, that payment complete messages are being sent and received from the payment system. All of these rules can be captured within a smart contract in a way that all the participants know exactly what's happening as part of their entire end-to-end claim processing business process. So, high level, at a very high level, smart contracts, they provide three key high-level benefits. That's increased transparency, improved efficiency, and reduced counterparty risk. And then drilling down a little bit deeper, smart contracts provide a single source of truth for all the participants. They can capture data validation and verification rules and do that in a way that all the participants in this transparent single source of truth way, so that not only is it storing data, but the rules for processing data and determining whether or not data is valid can be captured by smart contracts, and allowing all the participants to be on the same page as to how the data was processed, who introduced the data, etc. It's security, so they're backed by, in this case, blockchain technology, where we're using modern cryptography to ensure that they're being processed correctly, and that only the participants who should have access to the details have access, and that anyone who is introducing data to the system that they're identified correctly and they have the right authentication and permissions to do that and to process the data in some cases. It provides autonomies, cutting out the middlemen. So going back to swap execution facilities, you can now allow these banks to engage in the execution of their swaps directly in a peer-to-peer way. That clearly increases transparency, reduces risk, and reduces the costs. You don't have these fees that they're extracting. Cost savings, a big one, like as we saw in when you disintermediate, but then also when you're able to recover from in an automated way, process data and recover from errors, you now have fewer people having to do manual inspections, send emails and spreadsheets, trying to go on these expeditions to find the source of the error. And then lastly, the efficiency and error reduction. In some cases, you by catching the errors at the very beginning of the process, as soon as a participant is providing data, you prevent these errors from propagating through the rest of the system. So you have that also reduces costs. You have fewer troubleshooting expeditions, but you're catching the errors as soon as they're introduced into the system. That's smart contracts, the benefits of smart contracts at a high level. And now I'd like to set aside some time for questions.
Great. Thanks a lot, Sam. That was really insightful. So I would have 3 questions here with regards to the benefits you've talked about. You've mentioned data validation and verification as a benefit. Could you just go in detail to what the difference is of validation and verification?
Sure. Yeah. So you can think of in many cases, let's say you're receiving an invoice, what we call a validation check would be in some cases are called syntactical checks, but it would be a quick check to make sure that the data is formatted correctly. So does it have all the fields? Are the fields specified in the format that you're expecting? So let's say you have a date. You have a date field. So an invoice might have the date that the person, performed the service, and there are many different ways to format a date. And as part of your validation rules, you would check to make sure that the date is in a format that you're expecting. So validation would be these kind of syntactical formatting kind of checks, making sure the message that that the smart contract is receiving is in the right format that it expects. And then verification, we use that term to describe what some may call more semantic, application-specific type of checks. So in the invoice case, you may have a rule that every invoice that a supplier provides you has an invoice number that should be unique. So you should never receive, that might be a business rule, that the system should never receive 2 invoices with the same invoice number. So those types of rules where you're sort of an application specific, it's going beyond just is the date formatted in the right way, or is this field contained in the message? Now you're saying, okay, let's look at this invoice number and let's check it against all the other invoices that the system has processed. And if there is another invoice that has the same invoice number, then we're going to raise an exception, because it means the supplier has provided us 2 invoices with the same invoice number, and we don't allow that. The supplier is required to provide us a unique invoice number each time, and so verification allows you to capture those types of application-specific rules within the smart contract as well.
Okay, great. That makes sense. Thanks. And then you also talked about consensus algorithm. And I was wondering whether always all nodes take part, or if it's possible that sometimes only some take part in that. Because I know that there's that you can restrict nodes from seeing certain things, for example. So I was wondering if in that case still every node would take part in that consensus algorithm.
That's right. Yeah. So this is where it depends on what exact blockchain technology and what exact system you're using. So there's a few different architectures. A lot of so far we've been speaking pretty generally to apply to most permission blockchain architectures. But this is where you start to drill down into which actual permission blockchain system you're building on. So there are some permission blockchain systems like BigChain DB, for example, where every fully validating node executes every transaction. So every node would run the smart contract and would participate in consensus. And that's similar to how Bitcoin and Ethereum and Ethereum as it is now. There's some future versions of Ethereum where that's no longer the case, but that's sort of the traditional kind of blockchain. The first blockchains use that model. But now there are other, there are permission blockchain technologies, including Hyperledger Fabric, where not every node necessarily validates every transaction, and not every node necessarily executes every smart contract, and then furthermore, not every node participates in consensus. So you can partition your blockchain network into channels, for example, where you might have all the nodes within in a channel validate and reach consensus in that channel. But there might be nodes on the network that aren't in that channel that wouldn't participate in consensus. And then it gets even more complicated, where within a channel you have nodes that validate and execute transactions that then get submitted for ordering. So nodes participate in ordering and reach consensus on the order of the transactions. And the nodes that order the transactions don't necessarily have to be all the nodes in the network. So each organization might have 3 nodes, and only one of those nodes might participate in consensus, but all 3 of them might participate in execution and endorsing transactions. Anyway, and we should probably do another session to dive into the architecture of Hyperledger Fabric in particular, because it's more complex. But at a high level, no, it's not the case that every node has to execute and participate in consensus. I should also mention too that there's a concept of backup and redundant nodes, even in the traditional systems, where they are merely storing copies of the blockchain and not participating in consensus. So if you think in the Bitcoin network, most of the nodes are not participating in mining. Only a few groups have enough resources where mining is profitable. Now, all the nodes are still validating transactions, but they're not participating in this proof of work consensus where they're generating blocks and sending blocks throughout the network and collecting the mining fees. So we'll probably dive into this in a little more detail, but at a high level, it's not the case that every node participates in consensus.
Okay, great, thank you. And my last question is with regards to the benefit of cutting out the middleman. And I was wondering if that only applies to the public blockchain, or if that is also a benefit in the private blockchain, and if yes, how that would look like.
Definitely. So the two, so certainly in the public blockchains, when you have cryptocurrencies like Bitcoin, it allows, it functions as someone's bank. So their cell phone now becomes their bank. And, there was a famous quote about, each I won't misattribute it, but, it's a Swiss bank account in your pocket. Mm-hmm. And so clearly that, like you're saying, that cuts out a middleman there. But it also, in private blockchains, you can cut out middleman, as well. So we talked through the swap execution facility, which would be a private network of a swap execution facility and several banks together all on the same private network. And in that case, you can perform those functions directly between the banks, and that would be a private permissioned blockchain amongst those banks. But another case could be insurance fraud detection. So if you're looking for duplicate claims across multiple insurance companies that are competitors, one way you could do that is through a trusted third party. You could say all these insurance companies could agree on a fraud detection company to perform fraud detection services, and they could submit either their claims directly to that trusted third party, who would then check to see if there's duplicates, or submit signatures of the claims, some claim details, and they would all trust that the third party is handling their data correctly and safely. They're not selling their data to some of the other insurance companies or something crazy like that, or they're putting a lot of trust in that third party, and using blockchain technology and some of the work Luther has done, we can allow these insurance companies to run their own nodes and form a blockchain network and detect fraud between each other without having to go through that trusted intermediary, reducing, like in the case if you're worried about their customer data being resold, it reduces the risk of that because you no longer have to worry about that third-party organization. And also, like in many cases, a trusted third party could provide a solution, but the organizations can't all agree on who that trusted third party is. And by being able to do it peer-to-peer, they no longer have to reach agreement on all of them trusting some third party to perform those services.
Okay, great. Thanks, Sam. So that's it from my side with questions. Thanks for all the input on the benefits of smart contracts, and we're looking forward to the next session, which will be on blockchain and enterprise.